To co zacząć? To zaczniemy. To ja zacznę po polsku, a potem przejdziemy na angielski. Proszę Państwa, nazywam się Włodek Zadrożny. Jak widać, do stycznia tego roku pracowałem w IBM Research, a między innymi nad znanym projektem Watson, to znaczy budowa komputera, który odpowiada na ogólne pytania w dowolnej dziedzinie. A od stycznia tego roku pracuję na Uniwersytecie Północnej Karolinie w Charlotte. Pan rektor Żyłaski prosi mnie, żeby tu wykładać, no więc będę wykładał. I w takim razie przejdę na angielski. My name is Włodek Zadrożny. I work currently at the University of North Carolina in Charlotte. Previously, for 27 years, I worked at IBM Research on different projects related to text processing. I built several systems for text processing, including contributing to Watson, the system that played the Jeopardy game, won, and is currently being implemented by IBM for applications in medicine and in various other fields. So I will cover that in the class. So this class is about text mining for predictive analytics. So we're going to focus on text preparation using various machine learning techniques for classification. We're going to discuss text mining architectures. And all of that will serve as an introduction to better understanding of the Watson architecture. So we will answer the following set of questions. That is, what is text mining about? How language processing is connected with information retrieval or search, speech processing, and some other disciplines of artificial intelligence. We're going to discuss common applications of text mining and talk about some promising new directions. So today, main concepts. So get a sense of what is being done, what people are doing, what is possible, what is not possible. And we're gonna overview selected tools and techniques for text processing, just to give you a rough map of a very complicated landscape. So the topics can be viewed, we're going to discuss what does it mean to treat text as data or language as data. What are the algorithms for text processing? How are they used to give companies some competitive advantage? And Watson will be part of it. And some unsolved open problems also will appear on the map today. So we're going to start with easy stuff, all right? That is applications that involve counting words. We're going to review the Bayes theorem, and we're going to progress to more comprehensive models of language, and finally talk a little bit about Watson algorithm. So I have a question. How many of you know the Bayes theorem? No? Okay, so we definitely need to review it. And how many of you had probability calculus? No. Just regular calculus, for instance? High school calculus? No? Okay, so, all right, well, we're going to review everything that's needed. All right, so let's start. We're going to start with a discussion of what language processing is about. And the purpose of it is to introduce some vocabulary. So in general, natural language processing is an area that deals with interaction of a machine and a human using natural language or natural languages. Sub-areas, and we're going to explore these topics to some extent, although not machine translation and definitely not speech recognition. So we're going to talk later about parsing, which is taking a piece of text and finding a grammatical structure in it. We're going to talk about semantics, which is the search for meaning in text. Question answering, that's what Watson did. Dialogue, if we have time. There will be some of it, some glimpses of it today, but not much. Machine translation only will appear in passing because we will not have enough time for that. So this is a diagram, okay, that shows concepts, words that are connected with natural language processing. So algorithms, words, language, rules, meaning, syntactic, and a couple of other things, all right? So all of this will appear in some ways. So a synonym for natural language processing is computational linguistics. So what you see on the right is a book by Eugene Charniak, a professor at Brown University, who started or codified the field of statistical language learning or statistical language processing. He was one of the first people to build a statistical parser or statistical grammar. And this is a Wikipedia, a part of a Wikipedia definition. So computational linguistics is a field dealing with statistical or rule-based modeling of natural language from computational perspective. So it's not the traditional, what the traditional grammarians have been doing, but rather try to get their insight into a computational forms. And sub-areas include morphology, which is finding the structure in words, so prefixes, postfixes, and that kind of stuff. Parsing or syntax that we mentioned before, and semantics, dialogue, language translation, and speech recognition. So this shows that indeed these two names, computational linguistics and natural language processing are synonymous. So we can count words. So here we have, a number of words in Polish that you can all read, all right? The size of each word is proportional to each frequency. So the first puzzle of the day is, where is it taken from? Any guesses?
From a newspaper.
Okay, that is one pretty good guess, but not quite, yes. All right, so this is basically a text of Polish Constitution run through, through an algorithm which counts words and then displays them where the size is proportional to the frequency. So here we have the same thing for the American Constitution in different colors. Okay, so you can play with it at the URL that is given here. It's called wordly.net. It gives you some insight about what a document or a collection of documents is about. But of course, it doesn't tell you all. It doesn't tell you anything about the relationship between the states and the Congress, or amendments and president, yes? So we know that the Constitution deals with these concepts, but it doesn't tell us how they are dealt there. So counting can be used to do many things. So we can, by counting, we can see what documents are about, as in these two examples before. We can find similar documents or answer a query. That is essentially what Google does, yes. I mean, it's a very sophisticated way to count the documents and count links between the documents, which we're going to discuss. Machine translation is essentially a very sophisticated way to count. Okay, not only, but there is quite a bit of it. And more surprisingly, we can use counting models to help grade essays. That is, currently many of the many of the testing companies, such as ETS, which administers so-called SAT test in the United States. This is the test that you take if you apply to a university. Part of the test is to write an essay, and these essays are being graded by machines. And the quality of grading is as good as a human, okay, grading. So it's not exactly the same, but in terms of, you know, agreement between experts and the machine, it is indeed very high. So that is a good way to process a large number of essays that are submitted every year. But we don't have machines that understand language, and, you know, we try, I mean, many things have been tried, all based on counting. We don't have machines that can engage in a sophisticated dialogue, that can provide professional quality translation as opposite to gist translation that we can get, for instance, from Google. Or we don't have machines that can suggest improvements to an essay. So what's happening there is that the machine, by looking at the patterns, at the distributions of words in essays, can say, okay, well, these kind of patterns are associated with higher grade, and these kind of patterns are associated with low grades, and using these associations, well, they can assign a score. But they can't tell you that, you know, that if you did X, then your grade would improve by, you know, 3 or 4 or 50 points. So we are not there. Okay, I'm sorry. All right. So counting wasn't always sort of the preferred method of doing natural language processing or computation linguistics. In 1950s and 60s, 70s and 80s, an argument was made that the best way to understand language would be to have some representation of a reality, then map the words of a sentence, okay, such that the sentence here says, he wears a jacket because it was required, okay? So map the words such as he to the person wears, well, the situation where the wearing might happen. A jacket, here we have a jacket, and then, you know, there is some background information that says the jacket was required. So the idea was to parse the sentence, find the grammatical information, map it into some kind of a formal representation, and then this formal representation would be used, for instance, to do machine translation, okay? In the late 80s and beginning of the 90s, a bunch of people at the Watson lab, Peter Brown, the De La Pietra brothers and Robert Mercer published this paper called The Mathematics of Statistical Machine Translation. And what they did there was replace this kind of model, okay, the model where you have a grammar that drives the translation, by the model which uses Bayes' theorem, which we're going to talk about in a minute, to estimate certain set of parameters and create a translation from French to English or from English to French without any grammatical knowledge at all. On the other hand, they had quite a bit of data. That is, they had so-called Hansard corpus, which is the corpus that has proceedings of sessions of Canadian Parliament, which were given simultaneously in French and English. So if the person was speaking in English, it got translated by a human into French. If a person was speaking in French, it was translated by a human into English. All of this was available at that time on a very big tape, a tape of text, not just the tape of spoken language. So the text was available, and then by creating a sophisticated mathematical model of how the words are distributed, my colleagues at IBM were able to create a translation system. Okay, so this was a very big change that happened at the beginning of the 90s and got completed probably at the end of the 90s. So by year 2000, almost all work in computational linguistics was done using statistical means. Over the next 10 years, it turned out that that's not enough. So currently, we are mostly using some mixture of statistical and linguistic-based techniques. What you see on the right is something that happened in the late 90s. So any guesses? All right, so what you see on the right is an architecture diagram of the first Google system, okay? So Google happened basically at the end of the 90s, and this is the architecture of the first Google system. So a lot of stuff happened, okay? This is how the decade of the 90s started. This is what drove the statistical use, and at the end of the 90s we had Google, all right? So a very important decade in the history of computational linguistics. As I mentioned, the main tool that computational linguistics uses is the Bayes theorem. Okay, so we have here two people, and that's Reverend Thomas Bayes, for whom the theorem is named, and arguably he was the inventor of the theorem, but the real analysis and application to probability calculus was done by Laplace, and this is the other guy. The pictures are from Wikipedia. All right, so let's look at the Bayes theorem. So where do we start? Well, we start with a definition. This is an important concept, conditional probability. So how many of you have seen it? One? Anybody else? Anybody else have seen this sign? Probability of A given B? Yes, okay, great. And you've seen this definition. All right, so we can proceed. All right, so this is the definition, the probability of A given B. So it says that to compute the probability of A given B, so if B is, for instance, this B1, we divide the area of B1 by the area of A. If B is B2, we take this part only, all right, and divide it by the area of A. For B3, it's going to be empty, so this is 0, there is no common part. So this is the definition and the intuition behind the conditional probability of event or a collection of events A given B. So from this definition we can derive Bayes' theorem because the definition was symmetric. So if we look at this expression, yes, so probability of A given B, we write it like this. Probability of B given A, we write it like that. We have one common factor here, P of A times B. We can write it in two different ways. So probability of A and B can be produced from this formula as a multiplication of probability of A given B times probability of B, and from the second formula by the expression probability of B given A times probability of A. Well, that would suggest that the probability of A given B, can be obtained by dividing probability of A and B, probability of B given A, yes, this part, divide by probability of B. So essentially we take this part here, which is probability of A and B, and divide by P of B, which is this thing. Yes? Is that clear? So it's a natural mathematical transformation. So that is Bayes' theorem, and well, it's widely used. The common example that is given for the Bayes' theorem is the drug testing example. So we have a test that is 99% positive, true positive for a drug user, and also 99% true negative for non-drug users. Okay, so it's a very effective test. Now let's assume that only 0.5% of population are users of the drug. So now we take a randomly selected person and we ask the question, what is the probability that this person is a drug user? Is it 99% or less or more? All right, so we're going to apply Bayes' theorem to answer this question. All right, so this is the statement. Okay, so we have a 99% correct test, both for true negative and true positive. True positive, true negative. 0.5% of population are using the drug, and we want to estimate certain set of probabilities. So if we were to use the diagram from the previous slide, here we have the set of all people. Somewhere here we have the users. Somewhere here we have users who test positively. So, and non-users who test positively. So this thing is 1% of the area. What else can we say about it? Okay, so that would be the setup, and I will encourage you to go through this example later. But let's just finish the calculation just to see what numbers we're gonna obtain. All right, so again, 99% correct test, true positive, 99% for true negative, 0.5% of people are using the drug. So let's analyze the situation. If 1,000 individuals were tested, there would be 995 non-users and 5 users. From the 995 non-users, false positives are expected. And from the 5%, from the 5 users, true positive are expected. So we can expect that 99% of these 5 people will be tested positively, because that was the number here. And 99% of, and 1% of non-users would also be tested positively, because the test is not 100% here, but it's 99% correct for true negatives. All right, so if you plug these numbers, yes, what do we get? We get that out of 15 positive results, only 5, or about 33%, are genuine. Okay, so the probability that the average person will be a drug user is only 33%. Okay, so by plugging in these numbers into the Bayes theorem, what do we say? What do we see? We have 99%. This is the size of the population, 0.05. Okay, so the percentage of the population. Here, probability of user being positive times probability of user. We have this 0.05 times 99, and here we have the probability of non-user being tested positively, which is 1%, times the probability of a random person being a non-user, which is almost 100%, but not quite. So dividing these two, we get about 33%. We get the same result by sort of reasoning about it. So this is an important observation. It shows that the relative size of population matters, okay? And just because we have this very high probability, it does not mean that sort of if we take a random object from a population that it's gonna have a certain property, okay? And we can actually estimate relatively well what the probability of a random user or a random word or a random phrase from a population of users, a corpus of text, etc. I mean, what it's gonna be. So homework for this, all right, and I can assure you that we will have at least one question about Bayes theorem on the exam on Friday. I'm supposed to give an exam. You are aware of that or not? Yes? Now you are? Okay, and you were not before? All right, so anyway, so play with these numbers. So the homework that I would advise you to do would be along these lines. So take the example that we have seen before, but let's change the percentages. So drug tests generally produce false positive results in 5 to 10% of the cases, and false negatives in 10 to 15% of the cases. So they are much less exact than in the example that we've seen before. This is for instance, you can find it in various places, but these particular numbers come from WebMD. So the homework is to redo the above computation using lowest and highest of these numbers, that is 5 and 10%, and pick your birthday as, you know, as the percentage of drug users. So if you were born, say, on the 1st of December, you're gonna put 1%. If you were born, you know, on the 31st of July, you can put 31. All right, so why do we care about Bayes' theorem? Because it appears almost everywhere now. So we will see application of Bayes' theorem in the class. The reason I introduced it so early in the game is so that you can think about how this kind of reasoning about probabilities could be applicable in the examples that we're gonna see. But I wanna go back to the overview of text mining and language processing. All right, so why do we care? Because there is a lot of data, okay? There is this phrase, big data. There is also big text. A lot of data that we see is textual data. It's not the majority. The majority is probably images and video and sensor data. Nevertheless, a lot of interesting data is text data. So there are some numbers like 1,000 exabytes of data generated in 2010. So it's growing almost exponentially or exponentially. There is a lot of medical, financial, games, Twitter, news, Facebook data. All of these are textual data, all right? Or at least have textual component. We have two ways of interacting with large amounts of data. We can visualize, that is, interact using shapes, or we can analyze it. You can analyze words in the data, and that's where text mining, text analytics, natural language understanding, dialogue management, all of that stuff comes to play. And the terms that we use is data mining, machine learning, and they are important in both of these areas. Why do we care? Because if we can interpret the data, we can derive knowledge, and knowledge translates into competitive advantage. I would say that currently companies cannot ignore the data that they have. If they do, it's very likely they're going to be out of business. At least it applies to any large enough company. And essentially, you know, instead of saying time is money, we can say that money comes from data, and if you can interpret it faster, you will derive more money. So the competitive advantage comes from being capable of very quickly interpret a large amount of data. All right, so going back to the big picture, all right. Big data is high volume. It comes continuously. Currently, there is a lot of social media analytics work. So Facebook, consumer opinions. People are doing a lot of work in this space. There is money to be made. It's important for brand management, for customer support. What else can be said? And we essentially are in management. We are witnessing a transition from anecdotal decision making, that is from a manager talking to their counterparts in other companies, talking to their subordinates, reading, okay, and then absorbing this information and then saying, okay, I'm gonna invest, in this new place, okay, or I'm gonna build a factory there, or I'm gonna change the price from X to Y, okay, that's what management used to do. Instead of that, they basically say, okay, this is the data we have, and statistically speaking, I'm gonna make most money if I do X. So data analysis becomes the basis for decision making. So decision based on trends derived from huge amounts of text. And this is gonna be good for us. That's what these guys said in 2011. We are seeing this in practice, all right? And for you, okay, who are gonna be, graduating, working for the next 30 years or something like that, at least for the next 10 years, probably 10 to 20 years, there will be huge amount of work to be done in data analytics and text analytics. These are really very highly paying jobs. In the United States, I think a good data miner makes on average around $150,000 a year. The same person working for a bigger company probably makes over $200,000 a year. There is estimate of about 2 million positions in text and data analytics. I should say data and text analytics. Most of it is going to be in data, but a lot of it is going to be in text. That's just the United States. Europe is not that different, and Poland is not that different either. Okay, there will be a lot of stuff to be done here in Poland and in Europe and throughout the world in this very area. So the opportunity is huge. And some of these opportunities we're going to discuss. So fraud detection, risk analysis, healthcare research, government trends, customer support mentioned on the previous slide. So for instance, the first application that we did for the Watson question answering system had to do with customer support. That is, IBM is running call centers out of India. What is happening in these call centers is that the customer calls with a technical problem. The person on the other side of the line is trying to solve this technical problem. So the person can do a search, can look in technical manuals, and they jointly try to diagnose and solve the problem. This may take 10 minutes, which is rare. It can take 40 minutes, which is more common. It could take, a couple of sessions. So given the volume of calls and given that these calls are expensive both for the customer and for the customer support, if we can use Watson to minimize, the time spent on the phone or even just reduce it, say by 10 minutes per call, the financial impact on both sides, the customer side and the IBM side, is huge. All right, and we're going to talk about some other applications to the extent that our time permits later. So, what you should remember is that we're going to go from anecdotal decision making to decision based on trends. All right, so analyzing text is a huge opportunity. Social media analytics, that is customer opinions about products, will drive analytics into the mainstream. I think this has already happened. It will take another 10 years before the computer can read, so it's a fun time for innovation. So let me comment on that. What it means is that currently, of course, the computer can take a piece of text, divide it into words, do something with these words, and we're going to see examples of what machines can do in this class. But machines have no real comprehension of these words. They have very limited comprehension. We can use it for certain purposes, but we can engage with the machine in a real dialogue that would test the comprehension of the machine. These guys are saying it's going to take at least 10 years, may take longer. So until then, this is going to be a big opportunity for text analytics. After that, well, there will be some other opportunities of dealing with text. All right, we already covered these points. All right, so let me show you a little video. Okay, of using, I'm sorry, that's not what I want to do. I mean, this is the video, but I want to open it with a real player.
Hi, my name is Wirtualny, and this is my research project at Yahoo Labs.
Okay.
You all know Facebook like and share button. In fact, Facebook allows anyone to get the total number of likes for any URL. In this study, I show you some interesting values learned from Facebook. There are 25 sites in our dataset. For each of them, you can see the number of likes and the link to the top story. You can also sort our collection by any parameter. New York Times is the overall leader with about 7 million likes over 3 months. These days, many editors believe that publishing frequency is the key. Our data shows the opposite. Your top stories attract the majority of user activity. As you see from our measurements, NPR, Guardian, or Yahoo News can get half of their time by publishing only one story per day. It is very surprising to see what stories are the most liked and shared. In top 40, there are only 4 articles about actual political news and 3 about celebrities. The most common type of hit stories is opinion pieces. Why Chinese mothers are superior is the overall leader with 340,000 likes. Other common themes include lifestyle, photo galleries, interactives, humor, and odd news. Some websites display actual number of page views for every article. In this case, we can calculate what fraction of visitors are tweeting or sharing a particular story. Our measurements show that for every 1,000 visits, there are from 5 to 20 likes and tweets. Now you can guess page views of individual articles that do not show page views. To get a baseline estimate, take the number of likes and multiply it by 100. An example. We know that Chinese Mother's article has over 300,000 likes. Multiply it by 100 and you can get an estimate of 30 million page views. Sadly, web articles are basically lost 24 hours after publication. Our measurements show that over 80% of likes happen during the first day. Yahoo News has the sharpest decay of user interest, and gadget articles have the longest lifespan. But even in this case, new content can only be visible for 3 or 4 days. This is a visualization of New York Times headlines. The size of every word corresponds to the number of stories. The color represents the average number of likes received by stories on a given topic. Bright red for a lot of likes, dark blue for the minimum number of likes. As you see from this chart, stories about Obama or WikiLeaks are really popular at New York Times. Stories about Google or China are much less so. We have over 20 heat maps in our gallery. Press left and right to see them all. These heat maps can be used as a tool for demand discovery. You can also see what are the most engaging topics and the size of your competitors. Here we picked a few brands and visualized their coverage at several technology blogs. The stories about Facebook, Apple, Skype, and Kinect are universally popular. Coverage of Amazon, Windows, and Samsung is much less engaging. We can do a similar analysis of topics. Our data shows that keywords how, why, best, and future correlate positively with article success. Search journalism engagement, you have to ask yourself, why do I publish something my readers do not care about? In demand analytics, you should really know what are the topics of highest engagement in your area of focus. Social media optimization. At this moment, an average reader of New York Times shares only one story per year. A lot of room for growth here. You can find all rankings, heat maps, and large-size infographics at the website of the study. If you want to get an engagement heat map for your site or have any questions, please contact me by mail or Twitter. This study can be useful for many professionals in industry, journalists, editors, product managers. If you know people in these areas, please pass the word. Thanks, and I hope you learned something.
Okay, so that was the video. Can kill this. Go back to the presentation. So what you see there in the video so it was a simple study. The technique was counting words, okay, and mining data statistics, likes or sharing or that kind of stuff. So the statistics came from social media, so likes and tweets. Topics were measured by keywords, which was not sort of the most sophisticated way, but by sort of plotting keywords versus popularity using heat maps, it actually provided some useful information. It also measured type of media, okay, like text or video, versus popularity, okay? So, very simple study. There was nothing, how to say it, there was nothing there that required, you know, sort of higher mathematics. Nevertheless, out of this simple study came some very interesting recommendations. I have a proof that these recommendations were not known to people working in the industry. So for example, a colleague of mine working at New York Times, when I sent him this story, he said that it was very interesting and very new to the people at the New York Times. So the fact is that even sort of very important public media such as New York Times in the United States, at that time they were not aware of the potential of analytics to improve their handling of social media and their presence on the web. All right, so this is sort of the summary of the results that we had seen in the video. So frequency of publishing is not the key to popularity. One story can generate 50% of the impact. The stories, you know, decayed very fast. Politics and celebrities are not that important in keeping the attention. What is most important is opinion pieces. So this is what people want to orient themselves in the reality, not necessarily they want to know what the facts are. The facts are probably derived from some other media. All right? And the actionable insights is promote your best story. This is the key insight on the editorial side, and obviously invest in demand analytics is good because it means we all gonna have jobs. All right, so again, this is a study, all right? You heard it. I will post the Lifshitz video somewhere. You can also find it online. So what you may want to do as an exercise is sort of sketch the algorithm. So what it is that really happened there. What was the input to what Lifshitz did? What was the output? What were the 3 or 4 important steps in this video? So I'm going to continue talking, and then we're going to take a longer break, after this segment of the class is over. So my guess is it's another 40 minutes, maybe less. Is that okay? All right. All right. So what are the morals of this story? The value seemed to be in organizing the information. The data was public. Anyone could have done it, yes? Nevertheless, this was the first such study. Text analysis, any questions, comments? Questions, comments? All right. So text analytics is crucial for organizing any data with textual content or some metadata like photo or video descriptions. Simple techniques can be powerful, and the question is, what happens if we go to dealing with bigrams, okay, or trigrams? Yes, indeed, we can do much more. So, for example, trigrams are enough to do pretty good machine translation. All right, so another study here, medical analysis. So here we are looking at pairs of words, all right, and we are recording temporal succession. So for example, what we're gonna see here is that in the center here, we have the word I, all right? We have a transition from I to walked, so what it says is I walked to a place, all right? So I walked appears one, but walked to a place appears twice, all right? Because we have number 2 here, all right? And then place is followed by I in another sentence. So for instance, it can say I walked to a place, and then the next sentence might say, I woke up, all right? So it could be a description of a dream, all right? I hugged appears 7 times, yes, and then, hugged grandma appears 8 times, all right? So we have these kind of measurements of successive words. So we have a sentence here, I hugged grandma strongly, okay? I found grandma, okay, appears, at least 4 times, because this is how often we can traverse this path, all right? So this is the technique, all right? And this is a description of a dream or a description of some imaginary or something like that. Moreover, the size of these arrows is proportional to the time that happened, okay, between the words. So if words are spoken very fast, these arrows would be short. If they are spoken very slowly, the arrows would be longer, okay? That's so very, very simple technique, all right? Now, this kind of technique can be applied automatically or semi-automatically to recorded data, and can be contrasted with traditional interviews as a method of diagnosis. And what we have here is that traditional interviews quantify the severity of symptoms, and the traditional interview method, which is the only method that the doctors employ, is about 60% accurate. This new method, which takes only the patterns of words, that is, how many words are spoken, how quickly, and what are the topics, was 93% accurate. So what do we have? We have a huge improvement in the accuracy of diagnosis from 60% to 90% using a very simple methods, okay? Counting words and measuring the time between words. diagnosis here has to do with mental illness. So what you see here is the patterns for schizophrenia, which looks like this, for mania, which looks like that. Okay, so a lot of words spoken very fast. And this is sort of a control, sort of normal person. So we see, the differences between these patterns, and the machine can be used to essentially provide mental diagnosis, or at least augment human diagnosis. And that way improve the accuracy of diagnosis. All right, so this is relatively recent, from a year ago. The paper has been published in PLOS ONE in April 2012. The title is "Speech Graphs Provide a Quantitative Measure of Thought Disorder in Psychosis." Okay. This is the quote from the paper. I don't think I have to read it. The slides will be provided, so you can read it on your own. The authors also say that the same method seems promising in measuring the severity of autism and Asperger's disease. Okay, so semantic measures of similarity between words can be used to help diagnose these psychiatric conditions, okay, that affect emotional processing. So again, this is the paper. So we see that now, using bigrams, bigram data, we can actually do something very useful in medical field. So let's just, okay, so we've seen these examples. We're going to see some additional examples later, but let's just summarize what machines can and cannot do, just to provide sort of the relatively complete view of the field. So machine can do these pretty well. They can do question answering, where the questions are what, when, and who. This is sort of, Jeopardy was a little bit more complicated than that, but essentially the questions were what, when, and who. These were not easy questions, but they were factual questions mostly. But machines can do automated tutoring, so they can answer questions, how do I do certain things, why certain things are the way they are, and what would happen if something changed, okay? This requires some, more sophisticated intelligence, and we don't know how to program these into the machine. Machines do automated ad placement, yes? If you want to place an ad, Google will tell you how much it's going to cost you and where it should be placed for maximum impact. But machines can't automate job application process. That is, I can't go to LinkedIn, input my data, and say, find me a job. The best LinkedIn can do is take my data and send me a list of opportunities for which I can apply. All right, but still the decision, I would be making the decision, not the machine. The machines can analyze sentiment reasonably well. That is, they can say whether a review of a particular camera or another gadget is positive or negative, similarly for movies, but they can't summarize a New York Times column discussion. So this take, 500 comments on an article in New York Times and provide me with a view of, what people are saying. Machines can find, whether business conditions changed. So for instance, did the company open a new factory? Did they hire new people? Did the number of people decrease? So simple business intelligence. Similarly for financial data. Are the earnings higher or lower? But machines can't monitor for patent infringements. That is, someone comes with a product, I may own a patent on this product, on this kind of a device, the machine won't be able to tell me from, say, the product description that whatever is covered by my patent appears in this particular machine. So that is out of the question. Machines can suggest relations between diseases and, and drugs or genes or proteins. Yes, that is, go to a big textual database and find the links between, certain expression of proteins, the genes that participate in the expression, and chemicals or drugs that can affect the expression of these genes. But machines are incapable of automated drug discovery. They can help humans, okay, using, because of this, but they won't do it automatically. And as I mentioned before, translation exists. You can translate from Polish to English and vice versa reasonably well on Google, but it does not, the machine will not provide you a professional quality translation. So bottom line is that these are sort of what we could call shallow, where, having a lot of data, applying Bayes' theorem gives us, quite a bit of leverage. This requires some deeper reasoning. We don't know exactly what is required here. That's why we call it deep. And machines can do it. So the field is relatively open. Other examples. Well, search is working reasonably well, but summarization based on multiple sources doesn't exist. Speech transcription, that is speech to text, in airline reservation works reasonably well. Speech to text in a large domain, even with large amount of data, doesn't work very well. Okay, so for instance, I can call an airline company and essentially get myself on the airplane from, I don't know, Charlotte to Atlanta without talking to a human and even without typing anything. But when Google transcribes my phone messages, yes, someone is calling me, I am busy, or or my phone is not on, the phone goes to Google, Google does the transcription, and this transcription very often is not so good. Okay, I mean, I can get some of the keywords based on who's calling. I can guess what the call is about, but the transcription usually has a lot of errors, even though Google has very large amount of data, both textual data from which they can build the language model, and recorded data from which they can improve their speech model. So again, this is not a solved problem. Essay grading here, for instance, based on vocabulary, grammar, or style assessment, but tutoring a student to teach the grammar, the style, the vocabulary, that seems to be beyond. I mean, maybe vocabulary you can do it, but definitely not grammar and style. Solve algebra problem, yes, but teach algebra, no. Generate diagrams based on metadata, yes. Describe diagrams using words, not. Search of images by words, not very good. Dialogue, airline reservation is fine. Pass so-called Turing test, which we're going to talk about in a second, no. All right, so again, I mean, we don't know how to do it. We call it deep. Well, we know how to do that using Bayes' theorem. We call it shallow. So is it all about counting? The answer is no. All right. So for example, Watson cannot be done just with counting. All right. Because we also need the structure of the language and the structure in knowledge, okay, and the fact that text is about something. So we're gonna explore some of this in these classes, but I think today it's gonna be mostly about counting, even though, you know, counting is not sufficient. What can we say? What do we mean by structure? Okay, we're gonna go into this deeper in subsequent lectures, but essentially by structure we mean grammars, finite state representation of language, things like slot grammar, logical forms, the fact that words are not created equal, that is, there are nouns, verbs, adjectives, and that words can be put in phrases, okay, and these phrases can have meanings, all right? So that's what we mean by structure of the language, and we're gonna cover it. There is a structure in knowledge, okay, that is the texts are about something. So text can be related to other texts through bibliography or links or quotations, which can be measured through PageRank, which we're gonna discuss. Objects and people are related to other objects and people. So social entity networks have structure, and we've seen, you know, some exploitation of that in the Lifshitz story. And the wrong models of this structure can have serious consequences. So I don't know if we have time to go into it, but basically what I meant by that is it can be argued that the internet bubble in the late 90s had to do with the wrong model of the internet. You know, the idea that, you know, that it's going to be quadratic growth instead of n times log n created the internet bubble. So given that we have these people and objects related, we can do relationship extraction from text and sentiment analysis, and we're gonna probably cover more of relationship extraction and less of the sentiment analysis given our lack of time. All right, so to finish this part, let's talk a little bit about the Watson project, okay? So in the Watson project, we exploited language structure that is grammar, shallow meaning relations, n-grams, which is essentially 1 gram, bigrams, trigrams, up to 5. We had some knowledge structures, which is DBpedia, which is sort of a database version of some of the Wikipedia data, and Prismatic, which is relationship derived from textual data. A lot of machine learning, okay, and architecture and tooling. So we're gonna cover all of this in the class. So a few more words about it. So I really like this particular quote. I can't remember the author right now, but I probably have it somewhere. But the Jeopardy exhibition marked a milestone in the long-standing AI challenge of automated open domain question answering, all right? Well, actually, that's not the quote I had in mind. But in any case, yes, I mean, this is definitely something, you know, a machine winning against humans in the game that requires language skill is definitely a milestone. All right. So by the end of this series of lectures, you should be able to understand at some abstract level most of the techniques and components that appeared in Watson. We're going to see it on the next slides. And you should be able to do some experiments with many of these techniques as separate modules. And putting it all together into something that resembles Watson, that could do sort of question answering, would probably take a year or two for a team of people, but it's definitely doable. I mean, all the descriptions are in the open right now. You have access to them, and that could be actually a neat project to do. All right, so what is in Watson, and how much of it we're going to cover? All right, so let's go through this diagram. A question comes, all right? There is some analysis done on the question. That is, a relation is extracted. The main relation that we care about is what should be the answer? What is the type? Are we looking for a person? Are we looking for a location? Are we looking for a quote? What it is that the question asks about. The next step is take the words from the question and generate many possible candidate answers, okay? So search happens next, okay, here, all right? And we're gonna cover, some search techniques tomorrow, all right? From search, we get candidates. Then what happens is that we try to find evidence that supports particular candidates, and candidates with most evidence supporting them wins. So what happens next is another search from evidence sources, which basically are similar sources, except that the processing has been done a little bit deeper here in this pile. And evidence is scored, and then a model is applied, and the final score emerges, and the candidate answer with the highest score becomes the final answer. So this is a, somewhat complicated model of question answering. Nevertheless, we're gonna cover some elements of question analysis. We're gonna cover search, all right? And we're gonna cover application of the model through logistic regression. So quite a bit of this stuff is going to be covered piece by piece in these lectures. Now, Watson required a relatively big hardware, and the reason for that is the following, is that one question can have multiple interpretations from which each interpretation can generate multiple candidates. Okay, so we have here, say, 100 sources. Each source can generate many possible answers, so we get hundreds of possible answers. Now, for each possible candidate answer, we can assemble thousands of pieces of evidence. So the result is that many algorithms can be applied to many pieces of evidence, and unless you do it on a very big machine and in parallel, you won't be able to answer a question very fast. So for example, on a standard machine like this, yes, answering a Jeopardy question could take between 30 minutes and 3 hours, okay, and sometimes it didn't complete. And this is, well, this is, what is it? This is 8 gig of RAM and i7 processor. So something similar to that, except running Linux, okay? It gives you sort of 30 minutes to 2 hours on average. Here by doing it all in parallel, we can actually do it much faster. That is between 2 and 3 seconds. I mean, the amount of RAM here is also bigger. All right, so that is Watson. So this is a success of AI. Here is sort of something where the AI hasn't succeeded so far. There is something which is called the Lebner competition, which has $1 million in money and a gold medal, called the Turing medal. And the purpose of the competition is to build a computer that can pretend that the computer is a human. That is, you have a room, say, next door, where the judges are sitting. In this room, you have a collection of computers. Any judge can interact with any computer, asking questions like, how are you feeling today? And what's the weather like? What do you think of, of the last, of the game between Borussia Dortmund and Bayern Munich? Yes, any question on any topic can be asked, and the computer is supposed to answer that the way the human would answer. Now, the purpose of the judge is to decide is, the terminal, say terminal A, does it show the interaction between a human and a judge or a computer and a judge? And if the computer can fool the judges, the programmer who created that machine gets $1 million. So usually it takes 3 or 4 lines of chat to determine that, that this is a machine. That is, the machine cannot engage in a dialogue that lasts longer than 5 or 10 lines of interaction and fool a judge that long. So so this is, these quotes are from 2011, but that hasn't changed in 2012 or 2013. It's the machines are getting somewhat better, but there is not that much difference between what's happening now and what was happening in 10 years ago. So okay, so what do we have? All right, so this is, these are 2 slides from Seth Grimes, who's running a text analytics summit. So we are here, all right, and there is way to go, but we don't know how to get there, how to pass the Turing test. So we have miles to go. All right. So the questions that we would like to answer in this class have to do, should give you some intuitions about why it is difficult to pass the Turing test, what it is that, that text mining is about right now, how it is leveraged in Watson, but where do these methods fail? Okay, we have certain approaches, they also fail. There are some new ones, new applications. We're going to cover some of this. We're going to talk about the space of applications opened by Watson and the difficulties that we would need to conquer that we have no idea how to conquer to get to pass the Turing test. All right, so this is basically it. We have some time for questions, discussion right now, and these are the things that you need to remember from this class, okay, this particular lecture. That is, you should know the Bayes theorem, that there is a range of complexity. Simple system can successfully use counting. Complex systems use many techniques such as Watson, but also the Bayes theorem. There is a Turing test, what it is, and that no computer passed it. And finally, that there are many opportunities in text mining. So if you have questions, I would be happy to answer them now. Otherwise, we can take a break. Questions? No? All right. So, okay, how about a 10-minute break? All right, so let's start the second part of this lecture. So we will be talking about tools, concepts, and challenges of text processing. All right, so we're going to start with tools. These three books are a good point to start learning text processing. So Taming Text, as I said, it's discounted for you, and this is the newest book that describes algorithms and tools for text processing. So I recommend it very highly. Fundamentals of Predictive Text Mining. It's a textbook that can be sort of used on different levels. That is, it can be used sort of as an overview of various text mining techniques. It comes also with a piece of software. But there is quite a bit of math in this book, so if you want, you can go actually quite deeply into the, into the statistical aspects of text mining. But, going deeply into math is optional here. Finally, this is from probably mid-80s, but recently updated, is Natural Language Processing with Python. The book is freely available, and so is the Natural Language Toolkit that comes with the book, but you can also buy a hard copy of the book from O'Reilly. This is probably the easiest to use, is more linguistically oriented, and as I said, this is Python, this is Java, and this is also Java. All right. So, three books, there are many tools, all right? We're going to discuss some of them, but let's just list several of these tools. All right, so what you see here is UIMA or UIMA. This is unstructured knowledge or text processing architecture developed by IBM. It's the basis for Watson, and if you want to build a very large text mining system that scales to many machines, this is a good, that's definitely a good tool. Originally, it was developed by IBM. Right now is continued, the development continues with the Apache Foundation. Other stuff from Apache is Lucene search engine and a search server called Solr. OpenNLP, a collection of tools for text minings. We mentioned this, and this just a moment ago. Stanford Natural Language Processing Group has a lot of tools available. We're gonna see some of them in action in this class. For example, the topic modeling toolkit from Stanford is particularly easy to use. It's written in Scala, but it doesn't require knowledge of Scala, all right? Another very common tool is GATE, which is general architecture for text engineering. So this stuff is available, and I think I could recommend all of them. In this class, we're gonna be discussing Lucene and Solr. We're gonna be discussing some of the aspects of topic modeling, but for example, we will not be talking about GATE because we don't have enough time. All right, so a few words about UIMA. Maybe I can close this door. All right. If you choose to experiment with UIMA, this is where you get it from, all right? As I said, if you want to build something scalable, this is the way to go. And the main idea is to use declarative specification in XML to build, you know, larger systems from smaller components. So essentially you specify how you put componentry together based on a declarative type system that, you know, that is described in the diagram like this. Most of it is in Java, but it supports C++ and indirectly Python and Perl. It was used in Watson. It's not necessarily easy to learn, okay? I mean, this has, you know, the manual is that thick, so it's not easy to use, but once you learn it, it's a very, very powerful tool, okay? And there is a lot of, you know, freely available stuff that can be plugged into UIMA. NLTK, Natural Language Toolkit, that's the book, all right? It's a very good starting point for learning language processing. Very easy to use, okay, even for people who don't know Python. Covers all areas of language processing. The book is free, but you can also buy it. I'm going to use this in the next version of the class in addition to the current book that I am using. Okay, so for instance, I mean, this class, yes, is mostly, it's going to be mostly based on the book by Shalom Weiss and company on predictive text mining, but I think as Python becomes more popular, I think this together with taming text should be playing more prominent role. Okay, so we're gonna go through, you know, through some examples from this book in a minute. Another tool that I would highly recommend, which is not a natural language tool, it's a machine learning tool, is called Weka. Any of you have heard of it? No, okay. So that is possibly the most widely used machine learning toolkit. It's Java-based, very well documented, has implementation of all important machine learning algorithms, very easy to implement, to experiment with. And then, you know, once you get a real job, if you wanted to use Weka in a commercial way, there is a commercial version of it too, called distributed by a company called Pentaho. A few other, Lucene and Solar and Indri, we're gonna discuss these in the class. So this is in the search space. This is in machine learning and language analysis. It's Mallet. It is a toolkit developed by University of Massachusetts in Amherst, the computer science department. Stanford has quite a few tools. You can find links to available software at this URL. Okay, so there are, you know, there is stuff here. If you see something and you don't like, you know, Stanford version of it, you type the name of the tool or the type of the tool in Google, and you can find packages from other universities. So there is a lot of stuff. They are not necessarily all easy to use. All right, so the first toolkit is NLTK, and your homework, although I have no way of testing on the exam, but I would urge you to do it nevertheless, would be to install the toolkit. So if you type NLTK or you go to nltk.org, you will find the instructions to install it either in Windows or in Linux, and just go through examples in chapter 1 and chapter 2. What it covers, okay, the first 2 chapters cover stuff like text preparation, elements of predictive analytics, parsing. Later chapters deals with semantics. There is data that's associated with it that you can experiment it with, so it's worth doing. All right, so that's the structure of the book. So as you can see, here is, there is a discussion of what the text corpora are and what, lexical resources you can use, how you process raw text. This is mostly about Python. This is categorization, which we're gonna cover using something else, but again, I mean, it's worth playing there. Analyzing sentences, building grammars, that's definitely beyond this class. We gonna cover some of the meaning of sentences, but we will not have time to do it programmatically. All right, and then managing linguistic data, that's definitely out of the scope. So anyway, so this is something you definitely should consider playing with. All right, so these are the links. At this link, you will find these things: description of the package, installing the data, installing the toolkit. So all of that, you just follow the links. All right, so first steps in Python, okay, because I'm gonna show you how easy it is to do this stuff. So, okay, so Python, the syntax is very simple, you can just stuff like print hello class, it's gonna print something to the console. Sleeping is just sleep 10, but the function is, you need the import statements, so the import statements are from package import function, printing, basic operations, you can multiply lists or sets, all right, sleep. If you try to do something in Python, Google has an answer. That's, so if you need to go through the toolkit, this is sort of the easiest way to do it. So now let me just switch gears and let me just run sort of a simple demo. Let's see, is it here? Okay, so all right, so this is a very simple program that follows essentially the elements of chapter 1 from the NLTK, and they're just going to show you that, that it's indeed very easy to do. So what, oops, this is, why is it not visible? All right, let's just move it. All right, so what do we have here? So this is a simple Python, so statement hello class, import sleep, wait 10 seconds, show multiplication, and then, this would be the statements if we wanted to download the toolkit, but we're not gonna do it because I already downloaded it. So we're just gonna do import. We're also gonna need frequency distribution just to show some stuff. We're gonna be importing some texts, which are objects in Python in this case. Let's see what else is gonna happen in this. We're gonna print some elements of the text. We're gonna find, so here, we're gonna take one of these texts and we're gonna find when white and pale appear in the neighborhood, okay, I mean common neighborhoods for white and pale, so situations where they share context. Similarly for A and D, oh no, we are not gonna print these, this would be too many, but for instance, we can try to find if birth and death appear in similar contexts. Then we're gonna do some word counts, all right, which we discussed earlier, so we can create frequency distributions for all these texts that we deal, and we can ask the question, how many times does monstrous appear in Moby Dick, okay? So we're just gonna compute that part and print it. We can diagram words, so we can plot 75 most common words, and we can see also, you know, if we take the most common 75 words, how much of it is actually, you know, how many words are actually among these 75, I mean, how many, sorry, what is the percentage of all words that's covered by these 75 words? So now if we run it, let's see, so I'm gonna just press run module, and let's see if this is somewhat visible. All right, so as you can see, it's printing hello class, it's multiplied the lists as it should have. So the syntax, as you can see, is relatively easy. Yes, I mean so it's importing an LTK book. We have text, we have sentences in text. Text 1 is Moby Dick. Text 2 is Sense and Sensibility. The book of Genesis from Bible, inaugural address, chats, Monty Python. So we have all these texts, but we're gonna be dealing only with these 4 texts, all right? So there is, I mean, so the NLTK book comes with big repository of data that you can use to experiment with. All right, so so text 2 is Sense and Sensibility, text 4 is the inaugural address corpus. All right, so we are echoing what the texts are. And now we're gonna be looking for common contexts for words. Okay, so we see finding the same neighbors for day and night. So we have, for instance, a day off, all day or all night, every day, every night, every day in, every night in, that night period, that day period. Okay, so these are the common contexts. The day before, the night before, the day was, the night was, all right? Birth and death, from birth, the death of, the birth of. So these are the, you know, some of the common contexts. How many times the word monstrous appears in Moby Dick? Well, the answer is 10. And somewhere there in the background there should be some frequency distribution diagram. Okay, so let's see if we can find it. Okay, so here we have it. That is not exactly visible, but let me read it. So the most frequent words here are period, okay, and the of. I think that might, or maybe that is a comma. This is a period, and his, he. This I can't read. To, oh, I'm sorry, to. Could this be a period or a comma? I'm not sure. unto that said my, so essentially stuff that I usually don't count as words, yes, these are tokens, but not necessarily words. And the rest of it is mostly so-called stop words. That is the words that I use to connect other words but do not have much content by themselves. Then later, okay, with much less frequent, okay, we have God, Father, witch, tame, Lord, Joseph, Son, and so on and so forth. So there are some more context, words with more content. So you could see that that we have this kind of, distribution, which is called the zip distribution, which if we were to plot it on a log scale, it would be a straight line. So it's an exponential distribution, relatively rapidly decaying, and then a very, very long tail. All right. So we can plot these things in Python relatively easily and get some sense of the distribution of words. And here are the same 75 words, but out of 30,000 words, these 75 words cover about 90% of the most frequent 30,000 words. So a lot of stuff is just covered by words which do not have much content. All right, that's a lot of text. So what's the moral of it? That when we prepare text for analysis, especially when our analysis focuses just on single words or bigrams, that is collections of two words, we want to get rid of words like and, or, to, that, because they do not tell us what the document is about. Okay, so we usually delete these stop words. All right. So any questions about Python? I mean, the reason I am showing it is just to show you that that to start working with this toolkit is really very easy. Okay, and you're going to learn quite a bit about sort of language processing by downloading the stuff and then going through the book chapter by chapter. Questions? No. All right. So let's continue to the next topic. All right. All right, so we talked about this stuff, so I can just skip it. So we have import statements, building common contexts, counting words, some frequent words. So this is a version of this chart. So we put them in stop word lists. All right, so let's talk about some challenges. So even though it could seem that language is language and we have no problem understanding it, so the fact is that for machines there are many challenges. All right, data can come in different formats. That is, the simplest things could be that the text can be in ASCII, or it can be in UTF-8, or it could be in some other format. Yes, so the byte representation of language can be different, and that is often a challenge. It's not a challenge in language understanding, but it's a real challenge in in processing the data. More interesting is that language can be modeled in many different ways. So I already mentioned that we can have simple models, just take words and count them, and you can do some interesting things with just counting words. But you can also build, complex grammars. You can try to derive some knowledge out of textual data. So we need to say something more about, about these different models of language. Another challenge is that tools use different models, okay? So you have, we have many tools. I mentioned probably, a small number of very popular tools, but there is much more available online. Python libraries for text processing are relatively big. Perl has, a tradition of being used for text processing, and there is quite a bit of stuff on cpan.org. So there are versions of tools, so it's not necessarily easy to understand which tool to use for which purpose. There are different operating systems. Not everything that works on Windows would work on Linux, and vice versa. And many of the packages are freely available, and therefore they have only a limited support, okay? The good news, though, is that almost any issue that you encounter, somebody else encountered it before, so you can Google it and you can find a solution that way. Not always, but in 90% of the cases, this limited support can be addressed by Google. All right, so this is from Taming Text. So let's look at some of these challenges in text processing. All right. So we have different character encodings. I mentioned that. So you have ASCII, you have Latin, UTF-8, UTF-16, you have uppercase and lowercase, and sometimes it's meaningful, sometimes it's not. All right. We have punctuation. Okay. The period is not always the end of the sentence. Okay. The period can appear between digits and it means something else. It can appear in a mathematical formula and it means multiplication. So dealing with punctuations is not necessarily easy. If you have accents, yes, how do you transcribe from accented text into sort of the ASCII text which doesn't have accents? All right. Word segmentation. How do you tokenize, that is, divide text into words? What counts as a word? All right. Does mathematical formula like E equals mc squared, is it one word or is it multiple words? All right. What about, say, formulas that have dashes in them? Is it one word or multiple words? Still, I mean, the segmentation is relatively easy for English because with white space you probably solve 90% of the problems, but for instance, Chinese and Japanese do not have white spaces, so you have to segment into words based on something else. So it has to be more driven by knowledge or some statistical information. Assigning part of speech, is it a noun or a verb? I mean, many words can be both nouns and verbs, and we're going to see some examples. Use of synonyms. How do we shorten the words to its base form? So, for instance, Polish has, has cases, yes, has prefixes and postfixes, but for purpose of search, you want to go to the root of the word, yes? So doing it is usually non-trivial. All right, so these are some of the challenges on the simplest, that is, character and word level. Oops. So this could be, I guess, part of your homework is, how would you do stemming for Polish? Would you do stemming or lemmatization? Okay, so stemming is basically essentially chopping the beginning and the end of the word if you need to, and lemmatization is going to a dictionary and finding the dictionary base form of the word. So what would work better for Polish? Lemmatization of stemming. Any comments on that? If you would say, if you are building a search engine and you want to have, sort of limit the number of token types, would you use lemmatization or stemming? All right. So other challenges is how do we detect find phrases like quick red fox, all right? Or hockey legends Bobby Orr and big brown shoe. How do we find subject and verb-object relations? Sentence boundaries we discussed a second. All right, coreference resolution. Jason likes dogs, but he would never buy one. Okay, he probably refers to Jason, one refers to dog, but this gets much more complicated if you have longer passages of text. And then multiple meanings of sentence, we're going to see quite a bit of that in action. All right. Multi-sentence and paragraphs, that is, how do we understand what the author really wants to tell us, all right? How do we do summarization? Similarly, for meanings of the documents, can we summarize the document? And at the corpus level, we have a lot of data. How do we figure out what this data is about, okay? So we're going to see such examples when dealing with topic modeling, but essentially we can look at the collection of documents and then apply some machine learning techniques to see what do these documents tell us, okay? What are they about? Maybe we can find some, other worth reading. So you probably are familiar with these words, yes, in Polish, yes. So we have adjective, such as quick, okay, and red. Adverbials or adverbs are like adjectives, except that they modify verbs. Conjunctions, they join two words. And is a conjunction. Determiner, the, a are determiners. Every is a determiner. Nouns, classes of people, prepositions, verbs. So this is the terminology that we use in grammar. And then what is important in when discussing grammars is the concepts of the head, okay? Head noun, head verb. So for instance, in the expression, the lazy brown dog, dog is the head of the noun phrase. Jumped over the fence, jump is the head of this long verb phrase. Grammars are represented often by grammar rules, all right? So sentence decomposes into a noun which has a subject or is a subject, and verb phrase, and an object which is another noun phrase. Okay, so this is how we usually write grammars. This is sort of the formal use for describing the grammars. All right, so this concludes the introduction, and we can take a 5-minute break. All right, any questions? No to 5 minut przerwy w takim razie.